Hello, we are Team 4 engineers, and this is our final design for CE 483, Senior Design 2, Spring of 2020. Next slide. Our team is composed of 4 technical area leads and myself, Adam Ribley. Our geotechnical lead is Macy Larinaga, our hydrology lead is Christopher Flournoy, our transportation lead is Jesus Martinez, and our structure lead is Nicholas Stewart. I hold a position akin to that of a team leader. I help keep our team on task, and I foster communication and collaboration amongst the group. Next slide. For our project, we were given a 1-acre undeveloped lot in Nampa, Idaho. We were tasked with designing a 6,500 square foot multi-story industrial facility capable of efficiently processing commercial truck, load, and unload cycles, all whilst adhering to the City of Nampa codes regarding drainage on industrial sites. Next slide. Constraints that face any civil engineering project can be categorized into 5 groups as seen below. Our economic constraint, despite not delivering a final cost opinion, was cost minimalization. We were legally constrained to retain all stormwater drainage on site by adhering to the City of Nampa development codes. We also faced environmental constraints of groundwater levels, base flood elevations, and native soil properties. We were technically constrained by the functionality of the facility, most importantly being the logistics of site traffic flow. And finally, we faced some degree of social constraint by ensuring that we designed beyond the legal requirements of safety for all the facility staff as well as any pedestrian traffic. Next slide. Here, we can observe the undeveloped site as it was presented to our team. Our site is only accessible from the street on the eastern side, and a river flows in the north-south direction parallel to the western side of the site. There is a naturally occurring grade downwards from east to west of the site towards the river. Next slide. I would like to briefly introduce our final design before we dive into a detailed analysis of each design component. Our building footprint is oriented with the loading bay facing eastward. Our stormwater detention facility is located in the southwest corner of our site. One-way traffic flow will enter the site in the north, flow counterclockwise around the building, and then exit in the south. Each of the design leads will discuss the respective design components in further detail.
For the geotechnical portion of this project, I received boring logs for the site, which were developed from standard penetration tests conducted at depths 2 feet and then in increments of 5 feet down to 25 feet according to Idaho standards. From there, bearing capacities, settlement, and failure modes were calculated for the foundation. Geological cross-sections and pavement was designed as well. Next slide. Upon analysis of the strata underneath the building site, I decided a shallow foundation replacement would be the most cost-effective and practical. The specifications for the granular replacement fill is a cohesion value of 0 and a failure friction angle of 30 degrees at a depth of 5 feet under the grade. Originally, the replacement zone was 3 feet but was extended to 5 feet in order to ensure safety as well as ensure that if failure did occur, it would occur within the replacement fill and cause no harm. 2 types of footings were designed to support the load of the building. Isolated footings were all designed to carry the column with the greatest load to increase the safety factor as well as make it easier for the contractor to carry out this design. An allowable bearing capacity of soil underneath the isolated footings came out to be 5,771.65 pounds per square foot at a depth of 3.83 feet. The ultimate bearing capacity was then found based off of this design criteria. Combined footings were designed for the wall footings. The allowable bearing capacity of soil underneath these footings was 3,848 pounds per square foot at a depth of 3 feet, and ultimate bearing capacity was found based off of that design criteria. Next slide. The settlement design criteria for a shallow replacement under an industrial building is no more than 25 millimeters. Based off of the strata, loadings, and footing sizes of both the isolated and combined footings, the settlement values were all well below 25 millimeters, ensuring the settlement of this building will not cause any foundation failures. It is important to note that since a granular fill was placed, only elastic settlement is at play here. When designing a shallow foundation replacement, several failure modes must be considered to ensure the soil will not fail. General shear failure, local shear failure, and punching shear failure were all calculated under each footing, and they each passed with a factor of safety greater than 3, which is the standard for this type of shallow replacement and structure. Next slide. I have attached a geological cross-section for this site. As you can see, it includes the in situ soil of the site as well as the replacement granular fill placed 5 feet under the grade. It also includes the saturated silty sand which is under the water table. Next slide. This typical pavement section was designed for the entirety of the pavement on the site. We chose to design all pavement to support the load of the biggest truck coming onto the site while also making it easier for the contractor to place. According to specifications made by the transportation engineer on our team, the pavement is designed to have a 3-inch asphalt mix directly under the grade, a 4-inch aggregate base, a 6-inch granular subbase, and then 22 inches of subgrade soil. This design meets all design standards for this industrial site as well as the traffic expectancy.
Hello everyone, my name is Christopher Flournoy and I am our group's hydrology expert. Today I will be talking about the hydrology design portion, the design criteria that was used, and the results of our calculations and designs. Next slide. So overall, our hydrology design included the detention pond, the grading plan, and the pipe layout. The detention pond was based off of the flow net calculations that we came up with for the 100-year flood, and then the volume was taken from that and made slightly bigger in order to encompass all of the water flow that would come off the site during the 100-year flood. So the 100-year flood is an expected event that is basically the furthest, most extreme catastrophe you would expect for this site. So we're designing with factor of safety to contain all the water on the site as well so that we don't have flooding going off or having it going into the road or anything like that. The grading plan is basically a layout of cut and fill calculations that has all of our site's water going towards the detention pond. And the pipe layout was a layout that goes around the parking lot and encompasses all of the water and has it go towards the detention pond. Within that we had catch basins, T-pipes, and inlets. The next slide. So our design criteria was based off of the City of Nampa standards and the Idaho Standards for Public Works Construction handbook, which is, I believe we used the 2017 version, which is the most current version that we could find. So the first set of calculations that we did was the net flow for the 100-year event, which we determined to be about 4,000 cubic feet of water. So we made the detention pond to be about 30 feet by 30 feet with 3-to-1 slopes, which is standard within the Nampa standards. The infiltration rate of the soil is going to be at about 1/2 inch per hour. The bottom volume and area of the detention pond will be about 900 square feet, and it'll hold about 2,700 cubic feet at the bottom, but the total volume of the pond will be 4,500 cubic feet. On this next slide, you can see a side view of what the detention pond will look like. As you can see, the max depth water will be 3 feet, which is the maximum that the City of Nampa allows. The side slope will be at a 3-to-1, and there will be about 3 feet of uncrushed aggregate, which is according to the Idaho standard in section 801. That will be sitting on existing ground. For our next slide, you can see the grading plan and pipe layout. So the grading plan was decided to be about 0.5% slope across the site. So what that means is that we had most of our sections broken up so that they would have a 0.5% slope going towards either the detention pond or the designated catch basin / inlet that they were supposed to be there for. We determined that there would be about 100 cubic yards of soil that would have to be removed between all the different sections of our grading plan. The pipe will be 12-inch PVC, which is fairly standard in the City of Nampa, and will be sitting at a 0.5% slope. So that's going to be the slope of the pipe as it's coming around, and it will also include 2 drop inlets and a catch basin. If you look on our next slide, you will see a general overlay of what our site looks like. So if you'll look here, over the entire site, we have everything at a 0.5% grade. So on the left side, we have a 0.5% slope that will be going towards the detention pond, and that area will mainly be grass. Next to that, in the red, all of the red is the pavement sections. So the red distinguishes where we would have to cut the grade on a sloping towards the catch basin. The green represents where we would have to do a 0.5% grade away from the building, as you can see. And we have various catch basins and inlets throughout the site. In the top left corner, we have one drop inlet that will cover the top north half of the site. On the lower right half, we have another inlet that will cover the right side of the building and the parking lot. And on the bottom, we have a catch basin that will be installed into the side of the curb that will cover the bottom half of the building, the left side of the building, and the left parking lot, as well as the runoff from the grass on the right side, which is the bottom right side. As you can see, our detention pond is over here on the left, which is a 30 by 30, and all of the water that is coming from the top left side of the grass will be going into that. We wanted to originally do a site slope layout with elevations, but unfortunately our group was not provided with a survey plan that had all the elevations that would have been needed to put an extra layer over and develop a grade layer. So this is just an overlay of what it would look like if we were able to do that. The next slide you see is the standard details. These standard details are based off of the ISPWC 2017 standards, and we have one for catch basins and one for drop inlets. The difference between a drop inlet and a catch basin is mainly the placement of the system. The catch basin will be in a curb, and the drop inlet can be in the middle of a parking lot or anywhere on pavement. The next slide you'll see is a T-fitting, which is what it would look like having our two pipes combined. If you go back to the other slide where the general overlayout was, you'll see that the left side of the building has one pipe and the bottom right side of the building has another pipe, and there will be a connection of those two right before the drop inlet, or right before the detention pond. I apologize. And that's what our hydrology came out with.
Hello, my name is Jesus Martinez, and my part is transportation. So my portion of the project was the transportation design. Included in this was the parking lot, driveway, pedestrian ramps, signalization, traffic flow, minimum setbacks, pavement type, speed limits, and more. The criteria that guided my work was focused on safety and functionality. The results of my design were successful. I was able to produce a fully animated model, to calculate precise measurements, and deliver effective results for a client. The existing conditions at the work site in Nampa were minimal. There is a roadway on the east side of the property. This site is located in a GB1 zone, which means that it can be industrial or commercial use. The future of this work site has a traffic flow consisting of large 3-axle trucks, small trucks or vans, and regular cars. The max weight of the trucks is 80 pounds. These large vehicles require a large area for turning. In this case, the minimum radius for one to turn is 51.2 feet, which means the property must have an area that is large enough. This property will have a speed limit of 10 miles per hour. This is to ensure the safety of all workers who might be walking through the parking lot area. It will allow the trucks to have enough time to come to a complete stop if needed, based on their weight. property will have a total of 9 signs. There will be 2 speed limit signs, one at the entrance of the property, one about midway for trucks who have finished loading up and are preparing to leave the property. There will be also one-way only sign near the entrance to inform drivers of the property setup. I have also chosen to place 2 no idle signs to enhance this property's earth friendliness and also better for the workers who might otherwise breathe in the current emissions. There will also be signs warnings of pedestrian crossings at both entrance and exit. Since these trucks have very heavy, it is important to take all necessary safety precautions for pedestrians. I've also included signs near the sidewalks for the pedestrians, warning them of trucks entering and exiting, so they can too keep a watch out for safety. The trucks entering and exiting signs, as well as the pedestrian cross signs, will both be illuminated and flashing. The electricity will be sourced from solar panels on the top of the signs. The design of the parking lot was carefully tested on a fully working animation. The property will have an entrance on the northmost east side, which will be 20 feet wide. The exit will also be 20 feet wide and will be located at the southernmost east side. To encourage safety for the pedestrians on the sidewalks, the exit lane will have diagonal yellow lines to caution drivers to slow down before they reach the streets. Sidewalks will be 7 feet wide, which will allow more mobility for the people walking near this property. This property is expected to have approximately 46 vehicles arriving per day. This includes 12 axle trucks, 3 axle trucks, 10 passenger cars, and 24 trucks or vans. The traffic index is rated at 4.6. Since it's so low, the Idaho Transportation Department recommends setting it to 7.0. So we will go with that figure. It's pretty obvious that since there are going to be many heavy trucks, the pavement of the parking and driveway areas must be very strong and flexible. The type of pavement selected for this site is a flexible pavement. As you can see from the diagram, there are different layers which each have a specific purpose. I used several formulas when calculating the pavement design. I was able to determine the precise requirement to construct an effective parking area. And these are the numbers that came out with for the mix. The plant mix surface was calculated to be 2.68 inches. The aggregate base 3.36 inches. The sub base 5.37 inches. Subgrade soil 21.5 inches. This will provide a strong, flexible parking and driveway. The following is going to be a video showing you the fully animated design. For the setbacks, the Napa Transportation Manual states the setbacks that are required for the parking lot and also building must be at least 35 feet. There also must be 15 feet abutting a right-of-way to sign it as an arterial or collector. In addition, the city requires a 5 feet setbacks for the interior yard, parking, and buildings. With this, I conclude my part on the transportation design. Thank you.
Hello, this is Nicholas, and I am the structural engineer of this project. We have designed this building to be up to code and be aesthetically pleasing. With this design, we have also created a fully functional model which shows the extent of our design for the building. Next. This is a list of all of the criteria that was designed for the building. The list follows the design path from first to last. Next. These are the design criteria used for the steel portion of the design. Both ASCE 7-10 and IBC 2018 complemented each other in terms of design consideration, so that's why I used both. This slide shows the criteria for the design on both elevated slabs, floor slabs, and foundations. Next. As shown, we have created a fully functional model in Revit with the help from the design portion of the project. Next. For the roof design, we decided to go with a metal deck topped with insulation and asphalt. The roof will be supported by a joist and beam system of differing sizes. Next. For the elevated floors, we decided to go with the composite floor supplied by Vecro Deck. Due to the ease of installation, this was the most affordable solution for us. As for the columns, we decided that a brace system would be the best way to design for both notional and earthquake loadings. This all was done in Recit 2D. Given that the connections were not to be designed, a mold-resistant connection setup would be the best for this application. We also decided that a cross bracing would be necessary to reduce deflection and ultimately reduce the size of the material needed. Next, we decided an isolated footing would be the easiest and most affordable solution for a foundation design. The footing will meet the requirements for the frost depth and the factor of safety set by the geotechnical engineer.
Hello again, everyone. This is Christopher, finishing up with the sustainable solutions. The two solutions that we most wanted to implement for our group, but were not able to do, were the permeable pavement and stormwater swales. So permeable pavement is a pavement that essentially would be letting all the water from the site flow directly through it and back into the groundwater, rather than having to be contained as runoff that would have to go to the detention pond. The advantages of this would have been helping restore the groundwater, and also it would have reduced the size of our detention pond. The drawback that we found with this, though, is we didn't feel we had enough time to adequately research design for this site, so we decided against going with the permeable pavement. But it would be something we would recommend to our future clients. The stormwater swales were something else that we had come up with that would have been really good for an aesthetically pleasing site. And basically what a stormwater swale is it's multiple filters that have a native soil and native plants on top of them. So essentially it would filter out the pollutants from the parking lot or the drainage pond. So the problem we found with doing the stormwater swale is we didn't have an ideal place that would work with our grading plan to put our stormwater swale. So that is why we decided not to go with it. But if we were to revisit our site, we would probably redo that so that we could encompass that.
Two sustainable practices that our team would suggest our client implement can be seen below. Purchasing construction materials, especially steel and aggregates, is an environmentally friendly practice of reducing unnecessary shipment emissions. Recycling construction waste material that classifies as granular fill selected for shallow foundation should also be practiced. Next slide. In closing, our team has successfully completed foundation, pavement, stormwater, and structural designs for both our facility and site. We managed to realize this design while adhering to the client's requested design criteria and all safety standards and relevant requirements put in place by local and state governments. We believe that we have delivered a best value engineered product and that our client will be justly satisfied. Next slide. Thank you for your time.